So, as I've told people a few times, that there's no originality in this talk. This is an historical sort of talk. So, if anyone wants originality, you may as well just sort of leave or read a book or check your email or something else. So I'm hoping that the last part of this in particular can become sort of, I don't know how to put it, but maybe was the term Stuart Anderson one used, a little bit like a Quaker prayer meeting, where with Neil and Connor here, because they were both around the same time as the computing bit that I'm going to talk about. The mathematics bit was beforehand. So what I have in mind is talking about some little bit of sort of history of mathematics, basically, for the first half of the talk, and maybe a bit more than that, and then talk a little bit about how computational effects arose, which is what these guys might remember a bit, and they might have different memories to mine, and which could conceivably contradict what I have to say, which is fine, or might complement it, and say, okay, well, I remember so-and-so having said this, and I remember such and such having said that. And I remember thinking, so things like that. And just to give you a little bit of an idea of where this all came from, the sort of the computational effects, both from a mathematics perspective and then a little bit from a computing perspective, and perhaps how to think about it. Okay, so I think a sensible place to start is just talking about mathematics, right? So if you have, I think, pretty much any mathematics department at a university that certainly I know, and I'm confident that this speaks for a lot of the mathematics departments in Britain, in North America, in Australia, and that around year 2 or possibly year 3, but you'll have a course, to undergraduate students, a course with a name like abstract algebra, right? Or possibly algebra 2, or possibly with a name like groups, rings, and fields. Okay, now several of you, I think, did undergraduate mathematics degrees. Does this sound familiar to you?
Rings and modules.
Rings and modules. Okay, what year was that?
Year 2.
And what university?
Cambridge.
Okay, so Cambridge teaches rings and modules in year 2. Any other you did that?
Yeah, we had groups in year 1 and we had rings and modules in year 2.
And you were where?
Oxford.
Oxford, right? Okay, so there. And now, does anyone from any of the better universities, rather than these places that are finishing schools for the wealthy, right? So, Edinburgh groups, rings and fields in year 2. Any? Sorry?
Ring theory.
Right. Okay. This is all very interesting. I said this in Macquarie a while ago, and I said, year 2 these things happen, and they said year 3 here. So I said, well, at the better university, I mean, so, okay. And that's sort of an interesting division, right? Because we divided a little bit between groups and rings and modules, right? Because groups you associate with Galois, right? So Galois was the guy you particularly associate with groups, whereas pretty much any other algebraic structure actually came from Dedekind, right? So there was a difference. I mean, there was historically, groups, mid-19th century associated with Galois, rings, modules, a whole host of other things. Was actually came a little bit later. It was associated with Dedekind, and there's a very nice book. Actually, Dedekind's work. There are translations of quite a lot of Dedekind's work, and it's not unreadable, which is very impressive for something from 150 years ago, and it's well worth a read. Anyway, okay, so there's this understanding within mathematics, and so this applies to basically all mathematicians, will accept that there's something worth teaching at about year 2 level, which will include things like groups and rings and R modules So this is a coherent idea. It's accepted by mathematicians in general, that I think there's a standardized American Mathematical Society guidance on how to organize your undergraduate teaching, I think somewhere, and something like this is seen as a coherent body of work, right? And so that's accepted generally, okay? Now you get to a next point and you say, all right, well, so this is at undergraduate level. So we're going to call this year 2, undergraduate year 2, right? Now, then you could consider, what about making precise? What's the uniformity going on here? What makes these things unified, right? And that gives rise to universal algebra. So universal algebra is fundamentally about the unity of these ideas. And now it's quite a sophisticated body of work. It's not as common for that to be taught at undergraduate level, although I was taught it at undergraduate level. Is anyone else taught at universal algebra at undergraduate level? No? No, well, anyway, so I was in Australia, and I think it was fairly unusual there at the time, but certainly it would be sort of known work and somehow, even if not taught explicitly, sort of understood and with some sort of respect, at least at low-level graduate sort of stuff. And so this is where you get universal algebra.
Learn a little bit in model theory.
Right. And you were taught that at undergraduate level? Or
I guess so.
where were you for that? So Oxford Masters, they have a little bit of it. Yeah, a little bit of it makes sense. And in the context of model theory also makes sense. Anyone else remember being taught a bit of universal algebra? You were taught it in category theorem? Well, that's surprising. I mean, where did you get that?
In Munich.
In Munich. This is at an undergraduate level?
Yes.
Okay, so you taught it within category theory. That's a little bit more, that's a little less common because you tend to have either universal algebra or category theory. Universal algebra within model theory, I think is probably a little more standard. So then you have universal algebra, and that sort of makes this stuff precise. So then you sort of go, and this is sort of a more abstract direction or a more unified sort of direction. And you get here universal algebra. Now, that thing makes the unity here precise. Now, it does it in an interesting way. One thing that you notice is you make a distinction between syntax and semantics. That's a basic distinction that goes on in universal algebra. And you will talk about sort of operations. So, for instance, a group, you've got a binary operation, multiplication. You've got a nullary operation, which is the unit. You've got a unary operation, which is inverse. So by binary, it means x times y. You use an x and a y. For nullary, you've got this e, but it doesn't depend upon anything. And for inverse, it's x to the minus 1. You've got an x, and you get back an x to the minus 1. And for rings, you've got another binary operation for plus and another unary operation, nullary operation 0. And you sort of put these things together. In R modules, for each R, you've got an operation as well as the others. Okay, and then these are subject to equations. So each operation has an arity. Arities. So, and the arities, my writing has got even worse than usual there. Okay, and so at least rewrite that with arities. And the arities are natural numbers. As you said, binary, unary, nullary. So 2, 1, 0, right? Okay. And these are subject to equations. And the equations are necessarily universal, meaning they go along the lines of for all x, y, z, this equals that. For all x, y, this equals that. But it's always got to be for all blah blah blah, this equals that. That's That's what I mean by universal equation. So that's your syntax. Okay, your syntax is on that form, and then you'll talk about a model. So on the semantic side, you'll get a model. So your syntax will be sort of a sigma for operations and an E for equations, and then you'll talk about a model. So a model will be a set X. Now notice I haven't said anything about sets with this syntax stuff. So your model will be a set X, and for every operation, there would say alpha, you'll have a function from alpha from X to the n to X, where this thing is the arity of alpha. Right? So you've got a set together with, so when you had an operation with arity 2, you get a binary you get a function here from X to the 2 to X. An operation of arity 1, you'll get a function from X to the 1 to X. Operation of arity 0, well, X to the 0 is 1. To give a map from 1 into X is to give an element of X. Right? And that these must satisfy the equations. And this is a model, or equivalently an algebra. Algebra is probably a more usual term expression to call it when you're talking universal algebra, the algebras. Okay, and this is a model. Now, the distinction that's made here. So note this clear distinction: syntax, semantics, right? And this clearly unifies that, right? The definitions, the models. So a model of, say, the syntax, the sigma and E for a group is a group. A model for the one for ring is a ring. Okay, but you make this distinction here between syntax and semantics. Now, this has a few advantages to it. One is that you're talking, say, a model here, or an algebra, you're saying is a set X together with stuff. But, because you made this distinction between syntax and semantics, instead of saying a set here, you could say, well, let's say a topological space. Right? So you'd say, all right, well, a topological space, and we want a continuous function from, say, X cross X to X, etc. If you did that for groups, you'll get exactly the definition of a topological group. Okay? If you said, all right, well, let's do something a bit daring here and take, say, the syntax sigma E for a group and take the models in groups. Then you would have a group G together with a group homomorphism from G cross G to G, etc. Right? Then you have, and then there is the famous Ekman-Hilton argument, which says that to give a group, but with the algebras in groups, right, is the same as to give an abelian group. So there's this argument that says that if you do this, then your group structure is necessarily abelian, i.e. x dot y equals y dot x, and the group structure from here is the same as the group structure you get from there. So this was a theorem, Ekman-Hilton, around for a long time. So the universal algebra is giving you a little bit more flexibility, giving you some flexibility here, where you could talk about the models or the algebras in some entity. With our knowledge of category theory, we would tend to say in a category, right, of, but, if you're taught about this in an undergraduate algebra course where they don't assume you've ever heard of categories, they can still talk about it sensibly, right? But, so you've got this little bit more flexibility here, which is a nice lot of flexibility that you basically don't want to throw away, right? And you also see that flexibility in computing, right? That you would distinguish between a program and its semantics. I'm confident. I mean, you're welcome to disagree, right? I mean, but okay. So you've got that. Okay. So this is explicitly.
Since you invited scholars,
yeah,
I think it's very important because in programming language semantics, there's not one clear semantics. I mean, both mathematicians love sets.
Yeah.
But do we like domain theory? Do we like topologies? Do we like metric spaces? Do we like realizability? All sorts of different semantics. So if you want to have a understanding of meaning in programming languages, you've got to have this kind of flexibility.
Well, I agree with you.
Well, I agree with you.
Oh, thank you. Okay. Yeah, well, this is all getting a bit friendly here. It's starting to get slightly disconcerting. Is this grooming? Okay. Right. So, anyways, so you've got this clear distinction, and I think it's a very positive distinction that you don't want to throw away. You don't want to throw away for mathematical reasons. You don't want to throw away for computer science reasons, which I'm sure Neil and Connor understand in a deeper way than I do. Okay. Right. Now, mathematician will certainly buy, I mean, you'll inevitably get an occasional rogue, but they'll certainly buy that this is a unified block of work that should be taught at undergraduate level. Implicit in that is universal algebra, right? So they'll at least buy the principles of universal algebra. You need to buy the principles of universal algebra in order to decide that that makes a coherent unit, right? Even if you say universal algebra is not worth teaching at undergraduate level, I mean, you still have to buy the principle to find that coherent. Universal algebra then gives rise to a new question, right? And the question is this, okay? Take groups, okay? You can give different presentations, like different lots of sigma and e, for which the category of algebras, just using category, but you don't need to, but the algebras are groups. There is not a unique presentation. So you get a sigma and e, and you get a sigma prime and e prime, for which sigma e algebra and sigma prime e prime algebra are the same thing. They're the groups. So that means that the sigma and e are not model independent. You can have different ones which will give you the same models. Question: is there some syntactic thing, right, that is invariant? So is there some syntactic thing, let's call it, say, T for theory, is there some syntactic thing T such that if the T models and the T prime models are the same, then T and T prime are the same? Now, obviously, you're going to allow for isomorphisms, for change of order. Do you write down your binary operation before you write down your unary operation? If you're going to write down rings, are you going to put your times before your plus, or your plus before your times? I mean, you obviously want to allow for that. But I mean, is there something non-trivial here? Okay. Now, this is the question that Bill Lawvere studied in his 1963 thesis. Now, there's a great deal of misunderstanding about that thesis, including by people who really ought to have known better, such as McLean, right? Who thinks, oh, Bill has just written a thesis where he's given a category theoretic account of universal algebra. He did use category theory, but that's not the significance of the thesis. The significance of the thesis is that he answered that question, right? to give an invariant for the models. And this is where you get what he called algebraic theories and what I'm going to call Lawvere theories, for the obvious reason. You've got to think a bit about equalities and isomorphisms, but this is what it is. So I will write you down a definition of Lawvere theory. Right. Okay. So a Lawvere theory. What it is you get a small category L with finite products. Well, these finite products will transpire to be strictly associative. And then you get an identity on objects, strict finite product preserving functor, call it J, from the natural numbers op into L. Now, natural numbers op, okay. Natural numbers is equivalent to the category of finite sets and all functions between them. Finite set associated with natural number. That inherently has finite coproducts. so 0 is the initial object. If you've got, say, n and m, then n plus m is the coproduct of n and m. So since the category of natural numbers, or equivalently finite sets and all functions between them, has finite coproducts, then nat op has finite products. And so this is telling you, because I'm saying identity on objects, the objects of L must be exactly the same as the objects of nat op, which are exactly the same as the objects of nat. So they're the natural numbers. And the product is the product in there, in L, is given by the product in nat op, which is the coproduct in nat, so it's the sum of natural numbers. And so this is the definition of a Lawvere theory, and you consider that as syntactic. Notice we don't have, here we'd say a group would be a set together with something. So there's no set in here, okay? So this is so sigma E will give rise to a Lawvere theory L, and then a model of L, and you typically suppress, in writing, you typically suppress the J. Okay, that's not moving happily. A model of L in a category of finite products. Yeah, remember, we don't want to block the. Okay. And we also don't want you to break any part of your body. Okay. So the category of finite products, thanks. That equals a finite product preserving functor.
That's also a fine.
And
Get out the door, but not to the door.
Right over here.
that'll do. Okay. From L to C. Okay. So your canonical example takes C equals set. So this is your definition of a model of a Lawvere theory, right? And then you've got, go down here, and then you've got, for all sigma E, there exists a Lawvere theory, L of sigma E, such that L sigma E mod is equivalent to your category of sigma E algebras. Right? Which you have to do a little bit of work, but because we've constrained so much, we've said the objects of what the objects of L are, what the products in L are, then you realize after a little bit of thought, all you've got to calculate is what is L from n to 1. Once you've done that, everything else is determined, right? And then L from n to 1, that will be your set of n-ary terms factored out by the equations. And that's exactly what that's exactly how to calculate your L of n1. Okay. Right. Now, and this satisfies the question I asked in that if the mod, so this gives you a category, these are the objects, the maps and the natural transformations. And you've also got, so this is sort of what one might call sort of theorem 1, and you've got sort of theorem 2, that if you've got L mod as equivalent to L prime mod, well, that implies that L is sort of isomorphic to L prime. Okay. So you've got that invariance you're looking for with respect to models. Okay, so let's see. So essentially all mathematicians buy this, so they implicitly buy this, right? And there are people who study this stuff, and they're called universal algebraists. And they've written books, they've written papers, they're still around. I mean, there's schools of them around. But mathematicians in general implicitly buy this. natural question that arises from universal algebra, that I think any universal algebraist would recognize, is given invariant with respect to the algebras. This gives the answer to that. Right? So this is this is of interest to universal algebraists. Right? For mathematicians, they have to make another jump to get there, but they make two jumps rather than one jump. The universal algebra is already there. Okay. Now, not only do they sort of respect this, but then they took that, recognized that it answered a question, and then rewrote it in their own terms. I think it was Tarski, but it might have been someone else. Just re-expressed the notion of Lawvere theory as what's called an abstract clone. So if you look at the universal algebra literature, you'll find something called an abstract clone. Now, there's a little wrinkle about the empty set, okay, and empty operations, but that's resolvable, right? And has been resolved. But with that little wrinkle, an abstract clone is exactly just a universal algebraist expression of the notion of Lawvere theory, and with acknowledgement that it came from Lawvere. Okay, that by universal algebraic version, I mean they're not keen on using the language of category theory. And as I said, all the stuff in L, you're determined by what's L of N1. Right. Then you've got to think a little bit about the composition, but about how they compose. So they'll express it in that way. So rather than having L as a primitive, they'll have L of N1 as the primitive. Okay, but that's an abstract clone. So this is addresses a universal algebra question and gives an answer that universal algebraists respect as the answer to their question, that they'll simply rephrase it in their own terms. Perfectly reasonable thing to do. Okay. Haven't we all on various occasions? Yeah.
I think there was Africa.
So go for it.
Not that I'm not about theories are good. So at the end of theorem 2, there's a sneaky isomorphism.
Yeah.
L isomorphic to L prime, which is doing presumably some heavy lift.
No.
No? Okay. So this is kind of trivialized.
All it means is change of name.
Okay.
Yeah, are you going to call something F or F prime?
So what is preventing you from directly finding a notion of isomorphism or equivalence on sigma E pairs?
Well, you can, right? But the thing is, it's a non-trivial thing. Right. So it effectively amounts to saying, what do I mean for sigma E to be isomorphic to sigma E prime? Well, construct L sigma E, construct L sigma prime E prime, and ask for an isomorphism between them.
Which is exactly doing this.
Yeah, well, that's effectively what they have to do. Whereas the notion here of isomorphism is intrinsic. That on objects you have no choice. N is N, there's no choice. And all it's really saying is I'm giving an isomorphism between L of N1 and L prime of N1. And that just means change of names. But it's all in terms of L, rather than saying start with sigma E, build up L sigma E, then do this.
Thanks.
Okay, I mean, because that's inherently what it involves. It's a good question, right? But if you just say, what would be the natural notion of map between sigma E and sigma prime E, you'd say something like, all right, well, I want to function from sigma to sigma prime. I want to do something about E and E prime, and that doesn't do it.
Mm-hmm.
Because you first have to say, all right, well, I've got a sigma. I can't just have a function into sigma prime because I might not, could have different operations. I've got to build up all my terms in sigma E, sigma out of sigma prime, and then have a function from sigma into the set of terms generated by sigma prime.
At a high level, you could put it this way. Yes, there are other ways to do it, but in the end, you have those factor through doing this. You may not call it this, but you're going to have to do it anyway. So this is the best way to do it. It's not the only way, but it's the best way, and it becomes the only way.
Yeah, I mean, so you could express this in terms of abstract clones, but you're effectively doing the same thing, and they recognize that it's doing the same thing, just with slightly different languages. But you can't do it in an elegant way at this level. It's all right?
Could you say in computer science terms, the obvious arrows between sigma e pairs are kind of macro expansions. Like we're just translating one symbol into a bunch of symbols.
I don't think John could say that.
I think these guys could conceivably say it or deny it.
They're inherently local. Take one symbol in sigma, translate it to a couple of sigma prime. Whereas the L to L is a whole term translation. It can do anything you like. So, rename it.
Well, I'm leaving it up to these guys to respond to that.
I'm just trying to put in computer science. One's a kind of.
Do you guys have a response?
Be interesting to see whether there's something which forces the locality of translation. Do we know that that every such isomorphism gives rise to a kind of compositional interpretation of one signature into another?
I think it probably necessarily does.
I mean, the morphism from L's, like the function from L to L prime, that is this isomorphism, is a model of L in the category that L prime is, which is then, you know, if L is like L of sigma E, then it's a sigma model in the category L prime. So that means it is some sort of like for each symbol in sigma, some morphism in L prime, which is some, if L prime is also like L of prime, it's some composition of so they all have this form of taking each symbol in sigma to some composition of symbols in sigma prime and the other way around.
Yes.
So
Modular equations. on both
Yes,
sides.
modular.
right. So that basically means what we're dealing with are notions of interderivability, as opposed to having some sort of admissibility of operations, where you say, oh, there's some operator in one signature, and there's some non-uniform way to compute all the possible uses of that operator.
Do you have a question?
Oh, I just wanted to ask, I apologise, ladies and gentlemen, is this struck cider? No? No, okay, because getting lost. Thank you very much. Apologise.
Okay.
Sentence labeled 1 you have there, is that merely an equivalence of categories between
Yes.
models?
Yes.
Is there a way to see why it should be an isomorphism?
Yes. Okay. So you've got to think a little bit about exactly how do you define this and how do you define that. So I define this as the finite product preserving functors. Right? So you can't make it strict finite product preserving functors because I made these things natural numbers rather than finite sets. So if I had say a monoid, you run into trouble because the one must go to a one, and then you say, all right, well, and your product goes to a product. So if you said, all right, strict preserving functors, then it would mean the product in L must go to a specified product in the category of sets, and you run into problems, which means you don't have any models because they're not strict, because the finite products instead are not strictly associative. So you definitely want these to be the finite product preserving rather than strict finite product preserving. Whereas when you talk about sigma E alg, you'll have a set X together. You'll have a chosen X to the n. You say, I want an operation from, say, X to the 2 to X in, say, a group, X to the 2 to X. You'll have said, all right, what do I mean by that? I just mean the product in the category set. So you just wind up with these things being specified, the products there being specified and the products there not being specified. But like if you take, say, well, X and X in set, well, X cross X is a particular set, but anything that's isomorphic to it also acts as a product.
Yeah.
So that's,
But also, I think if John had written down isomorphism, you'd be suspicious because categories, notion of quality is isomorphism.
Sure, yeah. I'm just like in my head, like it was almost like models of L and sigma algebras should be exactly the same thing.
yeah. I actually thought that for a while and then realized I made a mistake. There are very occasionally in some of the things I've written mistakes because I've because I thought I could prove that something was isomorphic to something else, and then later realized, no, I could actually only prove it was equivalent. So I do have a few little mistakes around, but this one, this one actually, I claimed it to Max Kelly at one point, and he said he thought it could be otherwise, and then he tried to prove it and realized it can't. It's got to be an equivalence. Right. Okay. Right. So we're sort of basically reasonably happy mathematics-wise in this sense, in that mathematicians can't complain too much about this, right? Because this is standard, decent.
You say mathematicians can't complain about this.
Not too much.
I've heard them complain a hell of a lot.
Yeah, it depends upon the direction you come at it. If you give them this argument,
Mhm.
they're in a fairly tight corner
Mhm, mhm.
to get there. Whereas if you come straight at category theory or something, well
These are
then
my fault.
yeah. So it depends upon the specific argument. Coming at it, they must agree with this. They have to agree in principle with that. That this is a natural question that arises from that. About the invariance, and then here is the answer that historically was the first answer, right? And has been rewritten and has been accepted by universal algebraists, and there's a paper trail that shows it. That there are objective facts in there that they can't really complain about it. They may say, may claim, okay, you're introducing complex machinery to say something relatively simple. But as a matter of historical fact, that's the way it happened, and then you could say, all right, well, is abstract clone massively simpler than Lawvere theory? Then they could say, all right, abstract clone is simpler. But the ones who are going to complain most probably don't know that much about universal algebra anyway. So probably won't be complaining massively. But I mean, at least it limits a lot where their complaints can lie. Okay, right. Yeah.
Can I make a comment, which is that all of this is singly sorted, which
Yes.
is good for mathematics, but in computer science we care about multiple sorts.
Not in this case, you don't.
For the generalization to multi-sources.
Correct.
Something.
Yeah.
I disagree.
But yeah, I mean, the mathematics you can generalize to multi-sorts, but I mean, the computing stuff that was, the computational effects and that was all presented in terms of monads. I mean, that's historically what happened, and they had in mind monads on set or post set or omega CPO, something like that. And so they did not have multi-sortedness in that regard.
Modules of rings, fields are plain multi-sorted, and mathematicians care about that.
Okay, well, there's a precise sense in which our modules here are not multi-sorted. Because what happens is you take, for each element, little r of big R, you're taking an operation, L cross blank. So in this setting, well, this is the tradition. I mean, this is what's been done in universal algebra. You make plenty of progress from it. And vector spaces, are you really going to say vector spaces are not single sorted? That you fix your field, and then you take the vector spaces over it. So yeah, you can do these other things, but you'll see plenty of books which aren't particularly attached to category theory, which will talk about R modules as, okay, you fix your R, and then this is what the stuff that follows, standard stuff. And then you can say, all right, well, what happens if you've got a ring morphism from R to S? And so you'll quite separate out the role of R and the role of N. I mean, there's like two substantially different roles in there. So to think of it as single sorted would be more standard than thinking of it as multi-sorted. But in any case, as Neil said, you can deal with the multi-sorted stuff. But so I'll move on. Okay. So now the models of L in set. You've got a functor, so for any L, you've got a functor evaluation at 1 from there to set. And you could do this, like you could do this for a C, but that happens for any C with finite products. And then this guy has a left adjoint, say F, necessarily. With C, it also more generally has a left adjoint. You just need to put a few conditions on C to make it have a left adjoint. That's got a left adjoint. Therefore, you get a monad T, what one called TL, and you've got TL alg is equivalent to models of L in, well, I'll just stick with set, but you get that, okay? So up pops a monad. Now, a monad is one substantial step further away from the question we were asking, you know, and this actually, the step from Lawvere theory to model is quite a big step, because Lawvere theories, you know, you've made this distinction, you've still got this distinction between syntax and semantics. Your L is syntax, your models are semantics. Here, that distinction goes away. You've also got one of the basic constructions you want to make with universal algebras. You'll take the sum of the theories. So you'll take, you know, given a sigma E and a sigma prime E prime, you'll take sigma plus sigma prime, all the sigma operations, all the sigma prime operations, E plus E prime. You can do that in terms of Lawvere theories. There's always a sum of Lawvere theories that you can write down. The models of the sum of the Lawvere theories are the algebras for the sum of you know, signatures and equations. You can take a tensor product, which you want to do with rings, to get rings out of monoids and groups, or abelian groups. You take sigma E, sigma prime E, you take all the operations of sigma, all the operations of sigma prime, all the equations E, all the equations E prime, and you want sigma, the operations of sigma, to commute with the operations of sigma prime. That is the tensor product. You can take the tensor product of Lawvere theories, and it satisfies the same condition, and you can even write it down in a very elegant way. So I will write down as an aside here that, say, the models of L tensor L prime in, say, set, right, that's equivalent to the category of models of L in the category of models of L prime in set. There's a lovely characterization of the tensor product, lovely intrinsic characterization that, you know, sort of in some sense explains where this thing came from, right? It's the representing object. It's the Lawvere theory that satisfies this condition, you know? And also, you know, note how you're using the models of L in a category other than set, even when you're starting from sets. It's very elegant. All of this gets blown out the window as soon as you get to monads. You've no longer got your syntax semantics distinction. Sum of monads doesn't always exist. Tensor product of monads doesn't always exist. So all of this, you know, the constructions and you know, this delicacy is gone, right? Now, the reason is, right, that although every Lawvere theory gives rise to a monad, and every monad gives rise to the Lawvere theory, and if you start with the Lawvere theory, derive your monad, get back to a Lawvere theory, you get back to the same Lawvere theory. It's not true the other way around. Right? There are monads that do not arise from Lawvere theories. For instance, power set, you know, does not arise from Lawvere theories. And that is where, because you've got this extra bit of generality, your sum gets stuffed up, your tensor product gets stuffed up, and you're inherently already stuffed up your syntax semantics thing. So you'll have a lot more difficulty finding a universal algebraist who accepts that the monads describe universal algebra than you will with Lawvere theories, for the excellent reason that they don't. Okay, that they extend it and extend it in a way that you'll get lots of category theorists will fondly say, we have generalized universal algebra. Well, they've generalized the definition and meanwhile stuffed up a few constructions, you know? So,
John, I think it's worthwhile being more precise about exactly what they've fitted. You gave an example of power set, but what is it about the power set that fails to be presentable by operations and equations? I think they need to hear.
So there's a theorem which says, T arises from a Lawvere theory if and only if T is finite free. So this is a size condition, right? Which essentially says your monad, the behavior of your monad is determined by its behavior on finite sets, right? So more or less, it says take a set X, take all its finite subsets, take its image under all the finite subsets, then that has to determine the image of X. Yeah.
So hello world completely sinks all mathematics.
Sorry?
Hello world completely sinks all previous mathematics first. One of the first monads that I ran into was the IO monad in Haskell, which we used to, for example, write a program that prints hello world and straight
Okay.
confirm that your program is working. That's enough to completely mess up previous constructions.
Right.
I've never written that program.
But very
The
good.
point here is that when you do universal algebra, you've got these operations, and they're all have finality. You could never use an infinite number of variables in a finite term. And when you go to monads, if you drop that finality condition, you have this extra generality. But that extra generality means all these things aren't true anymore. So that's the problem
Yes.
of the extra generality. It allows-
Monads are too much for hello world. So,
They don't model what you're trying to model.
Okay. So this is what I was going to say about the mathematics. Now, then you get the computing. So what happened is in about 1989 or so, at his, or maybe 87, at his oral defense, Eugenio Moggi proposed monads as notions of computation. Now, I don't think he ever gave, or still hasn't given, an intrinsic definition of what do you mean by a notion of computation, other than saying monad. Nowadays, one typically say computational effects. Now, it's a little odd in that, you know, there'd already been operations and equations around in programming semantics for a long time. Right? So you know, there'd already been this appreciation of universal algebra in some sense, you know, algebraic specification, but also if you looked at, say, the book of Glenn Winskill, the book of Matthew Hennessy, the book of Bob Tennant, or even in, okay, not semantics exactly, but Robin Milner's book, and also, you know, Plotto with the structural operational semantics, you see operations and equations all over them. And so you think, all right, well, that would be a natural thing to sort of think of. That's the way you think about programming languages. But nobody, not only did Eugenio not come up with that, you know, he came up with monad, right? But also nobody seemed even to notice it or to care about it. Oh yeah, Smith and Hall with their power domains as well. Okay. Now I think the thing is that Eugenio's thesis was about partiality. Now, partiality is a finite monad on POSET, right? But I think it would be a bit unusual to think of it in terms of operations and equations. You more think of it as just partiality. You know? So maybe because of that he came up with this idea of monads to model things like exceptions and side effects and interactive input-output, as well as non-determinism and probabilistic non-determinism. So this was sort of the idea, but it got sort of definitional. And he never could, and I mean, people keep talking this really bad work about, say, monad transformers and that. And if you actually look at the definition, it's just dire. Right? I mean, I think they define what's a monad transformer. It is a function from the set of monads to the set of monads.
Sorry, I didn't hear that.
It's a function.
No, the next sentence where you wiggle your eyes and never said anything.
Okay. You know, I mean, and you think, how can anyone possibly be taking this seriously as a mathematical foundation for, you know? Okay, but at any rate, so you had this thing. I mean, there are good aspects to it. I mean, it did bring a sort of unity to that had not previously existed. And so yeah, there are positive aspects of it that still exist. but it's also sort of superficial in that you could no longer give you couldn't give a reasonable account of combinations. You did not have, say, a structural operational semantics flowing out of it. You couldn't do the sort of constructions that you would historically normally have done when studying programming semantics, where you say, all right, well, here are our term forming things, and here are some equations, or here are some operational semantics, and this we're doing in a unified way. And so the situation sort of got stuck with people tending to repeat the same thing again and again, sometimes in slightly different language. You say things like, I'm going to build a logic for computational effects. I am going to encode computational effects, that sort of thing, without any real conceptual development going on. That happened for a while. Now, but then one can notice, except for continuations, R to the blank, every example they had was, if not finitary, right, had a rank, which is in particular, if you extend finite to countable. They were all had the countable version of finitary. So in all of the examples, you knew there necessarily exists a Lawvere theory. There necessarily exists operations and equations that give rise to the monad. I mean, there's a theorem that says these things exist. Okay. The problem with the theorem is that it doesn't give you a good construction. I mean, it says there necessarily exist operations and equations, but if you look at the construction in the theorem, there'll be infinitely many of them, and they'll all be derived from your monad itself, right? But that's not what you're looking for. You're looking for like a finite number, computationally natural, maybe countable, but computationally natural, and equations that are computationally natural. If you took something like non-determinism or probabilistic non-determinism, these things were already known, okay? So they knew that, but then one could say, all right, well, they're a bit special. That exceptions was trivial, because you've got blank plus E, you just say, all right, well, we sort of raise E many exceptions, so you've got some nullary operations, that's fine. So the heart of the question came down to where does this monad S cross blank, where's that come from? Okay. Can you give computationally natural operations and equations that give rise to that? Where S is a set of states, so it would typically be a countable set of values, maybe natural numbers, and a finite set of locations. Okay. And you're asking, can you give natural operations and equations that give rise to that? That took us 12 years, right? But we finally got there, right? And funnily enough,
Can I ask John, was that because, how did those 12 years go? Did you sort of know the answer quite early and it's just difficult to prove? Or did you make mistakes? Or did you get part of the way there? You were missing one equation, one operation? Because the nice thing about
none of the above.
Okay.
We just couldn't think of it.
Nice. Because in retrospect, I remember reading the paper thinking, oh, fabulous. And I always think the way to push myself and test myself to understand something is to think, now I know the answer, could I come to the answer? So the operations, as you said, they all look natural, intuitive, and the equations, they look natural, intuitive. So with hindsight, one could have made decent progress.
I don't think so. What happened is that Plotto and I wrote a paper giving a generalized operational semantics that covered non-determinism, probabilistic non-determinism, combinations of them. And then Plotto presented it at this, he was invited to speak on something like FOSSAX in 2001 in Geneva. And Eugenio was in the audience, and somehow the question came up in the question session about state, having done it for non-determinism, probabilistic non-determinism, and this necessarily involved, here are these operations, here is your operational semantics that flows from it, which Plotto already liked. And Eugenio said, well, why don't you consider look up an update? I'd never heard of lookup and update, you know, at least to the best of my recollection. And so, you know, we get back to Edinburgh and I asked Plotto, what a lookup and update? What's he talking about? And then he sort of just wrote down for me what lookup and update are. And then we both went home, and the next morning we both came back with, you know, lookup and update as the two operations and with equations. He had one fewer equation than I did, but it turned out that I had exactly his equations, but I had an extra one that he proved was redundant. And we'd simply gone written them down, and that was it.
So once the penny of lookup and update as the operations hit, then the equation.
That's right. I mean, as soon as, you know, like I'd never heard of them, to the best of my knowledge, to the best of my recollection, I'd never heard of them, and that as soon as I heard of them and asked Plotto what they were, then, you know, and then Plotto, I think, hadn't realised the significance of it until I must have told him, because he went home and did the same thing as I did. But then, you know, it was just overnight, and it wasn't a hard calculation. It was just to know, look up and update all the things to consider. And then we just sort of cheerfully. Now, I did it just in terms of S, he did it in terms of V to the L, or I think a few days later he came up with a V to the L thing, because you think it's computationally more natural than just having S. And then it was funny, really, because we wrote everything down in terms of V to the L, and then Paul-André Méliès later wrote a paper saying, oh, this can all be done in terms of S, you know, which of course we already knew. But then he did find that one more of our equations was redundant, which sort of Plotto was pleased by that. I didn't really care. I mean, that once you've got a sort of small finite number of natural things, you know, so one of them say if lookup of lookup is lookup, you know, so if you look up L and then you look up L again, it's the same as just looking up L. But then there was another one which says if you update L by V and then update L by V prime, that's the same as updating L by V prime. And I think Paul-André noticed that one of those is redundant. Either the update one or the lookup one of them was redundant. So you think, okay, fine, but they're natural anyway. I mean, so I'm not too bothered. But at any rate, so that's what happened. So we all sort of wrote it down in terms of that. Once we'd written it down for state, we then had, you know, by that stage we had state, non-determinism, probabilistic non-determinism, exceptions, partiality you can write down without any fuss. And then Plotto came into my office at some point, because they'd had this big, long, complicated thing for as the monad for interactive input-output that I'd never bothered to sort of give much thought to, because it had you know, it had some recursion built in there. And he said, that is freely generated by read and write with no equations. So I said, fine. And sort of just, I assumed he'd known that forever. But in fact, he'd spent, you know, quite a while thinking about it. So I sort of only realized later I'd somewhat underestimated the work he'd put into that. But so then we had read and write. And then you start thinking about combinations, and you get the sum and the tensor, and they're working out to be exactly what you want them to be. So you know, put state together with almost anything else, you'll want the tensor product. You put exceptions together with almost anything else, you want the sum. And then comes the question, well, what if you take the sum of state with something else and you come up with something that's a little bit unusual, but Plotto believed was computationally interesting, where it allows for a bit of snapback, you know, to do it. And so that's where we got to. And then a bunch of stuff followed from that. And then there's a handless, of course, go from that. Yeah.
What is lookup and update?
Right. This is one I've rather conveniently written down.
In theory, this is the end of the term, so you know, we can quickly.
Yeah, whatever.
Conclusion, or we just jump to questions.
Yeah, I don't have anything to conclude. I may as well just answer his questions. So whatever you like.
Just
okay. So what you get is you get this thing A to the V to A to the L, and that's your lookup, A to the L, and that's your lookup, and you get an A to the L cross V, and that's your update. And you think, all right, well, where do these things come from? So the idea is that you know, given an L, no, so for lookup, given an L, you look it up, you get a V. Let's get you back to here, right? Okay, and then and for update, given an L and a V, you put that V equal to the location, equal to the value of that location L, and then you just go.
So this is in terms of the visual.
Yeah, you can express it. You can express it explicitly. When you think of, so a way to think about this is put A equal to S cross S to S cross X to the S, and then when you do that, you'll see it is completely obvious. So these things are doing is look up and update.
And then you realize that every program can begin by looking everything up exactly once, whether it's going to use it or not. And then doing a calculation based on those looked up things, and then writing every value back at the end. That's where so the equations allow you to normalize a program in that way.
Right. Yeah.
So that's to say, you know, you can get exactly functions from
Yeah.
Yes.
Okay. So yeah, I did write a total of 3 papers with Plotter, with 2 of them alone. The second half of our paper about state, combinations that did talk about local state, and I wrote a couple more papers. I did not get the result that I wanted. Right, I went as close as I could to getting it, and that because I wanted very much to retain this syntax semantics distinction. Okay? And so there is a monad for local state. It's on a pre-sheaf category. Right? And so we did have something which was where you've got a couple of tensor products around, because what you do is you have lookup, update, and block. And so this, and then you've got a couple of tensor products around, but they didn't want to have a couple of tensor products. They wanted to just have the product, hence the later 2 papers. But so what the local state means is that at any point you have a finite number of states, but you can add states, right? So you don't have an infinite number of states, infinite number of locations. So you don't have an infinite number of locations, but you have an arbitrarily large finite number in which you can add to, and that seems to be the way to go about it.